Today's customers are more knowledgeable than ever in terms of vehicle operation. The sales professional has to be familiar with how the various components of a new car or truck work and why they've been designed the way they are in today's Chevrolet products. The following disc program breaks down vehicle operations into 6 major areas: energy, power transfer, and aerodynamics on side 1, handling, weight management, and space utilization on side 2. Each of these areas is examined in terms of present-day technology and application. Energy, unharnessed, powerful, explosive. Energy of such magnitude that it transcends the frigid darkness of space through millions of miles to warm our planet and sustain life forms. And within these life forms, this energy of the sun is stored. And even after they die, the energy remains for eons underground. The energy is stored in various states: solid, gas, liquid, all with the ability to unleash the power of the sun through combustion, burning. And with coal, a solid substance, fire will ignite it. The same is true of its gaseous state. But with crude oil, combustion's a little more complicated. Crude oil will not readily burn until it's been refined. This results in gasoline, a product capable of sustaining usable combustion. The energy stored in just this amount is equivalent to the explosive force of a stick of dynamite. This combustion can only take place, however, in the presence of oxygen. Gasoline is, by its nature, volatile. It readily combines with air, forming a highly combustible mixture that can unleash tremendous power. This power is harnessed by the internal combustion engine and converted into rotary motion that's needed to move our vehicles. The internal combustion engine has been around for a long time, and while other designs have been explored, they've yet to prove themselves superior in terms of efficiency and dependability. And over the years, engineers have found many ways to make it better, more efficient, and more economical. One of the most critical areas of research involves the combustion itself. Now, this is particularly important because only 15% of gasoline's potential energy is used to power the vehicle. Most of the energy is lost through heat dissipation and exhaust gases. The quality of combustion, that is, the power generated from it, depends on the mix of fuel and air. Too much fuel makes the mixture rich, while not enough is a lean condition. The result from either circumstance is the same: inefficient combustion, poor use of fuel, and sacrifice of power. One of the main thrusts of research and development has been to find ways to control the air-fuel mixture more efficiently. Engineers realized that the conventional carburetor systems were physically limited in their ability to monitor this mixture. So they pursued new avenues of research. Reaching into the world of microprocessor technology, they developed a computer capable of analyzing data at thousands of calculations per second. This allowed them to design a system that determines the correct air-fuel mixture with the necessary accuracy to maximize combustion throughout the engine's performance spectrum. The computer must rely on data, such as engine speed and exhaust gases content, to make the correct determinations. This data is fed by a system of sensors, which is processed and fed back to control devices on the engine and transmission. A great deal of data must be processed, even for the simplest engine functions. Take idle speed as an example. The computer receives inputs of engine coolant temperature, battery voltage, vehicle speed, engine speed, air conditioner on-off status, transmission and gear or neutral status, throttle position, manifold pressure, and whether the starter is cranking. It analyzes this data and signals the idle speed motor to position the throttle to provide proper mixture for the operating condition. This system has introduced new standards of precision and accuracy, made possible with the advent of computer technology. And this is only the beginning. As we look to the future, microprocessor technology will account for even greater applications in the management of our car and truck systems. With the introduction of microprocessors that can control functions at high rates of speed, engineers began developing fuel control systems that could respond accordingly. Well, electronic fuel injection is just such a system. It precisely meters the correct air-fuel ratio by responding to on-off commands from the computer. The number of on commands the injector can get from the computer determines the precise amount of fuel entering each cylinder. Now again, the computer monitors the conditions of engine load, RPM, and the amount of oxygen in the exhaust gases before calculating the number of pulses required. Efficiency has long been a hallmark for another type of internal combustion engine, the diesel. Diesels share many characteristics with gasoline engines, such as cylinders, pistons, and valves. But there are key differences in a diesel, such as fuel injectors, pre-combustion chambers, electric glow plugs, thicker walls, and heavier duty components to withstand the tremendous heat and pressure. To better understand the differences between the gas and diesel engine, let's first see how the gasoline engine works. On the intake stroke, a mixture of both gasoline and air is drawn into the cylinder. On the compression stroke, this mixture is squeezed to about 1/8 of its original volume. At the beginning of the combustion stroke, this highly volatile mixture of gas and air is ignited by the spark plug, and the explosion forces this piston down. The diesel engine burns fuel in a different and more efficient way, without the use of a spark plug. At the start of the combustion cycle, the cylinder is filled with only air as the piston moves downward. This air is then compressed by the piston to 1/22 of its original volume, generating tremendous pressure and heat, approaching 1,000 degrees Fahrenheit. The less volatile diesel fuel is then injected, and because of the extreme heat of the compressed air, ignites instantly without the use of a spark plug, burning evenly and completely. Diesels are known for their economy and efficiency. But what accounts for that? What makes this engine more efficient than its gasoline counterpart? Well, part of the answer is the higher energy content of diesel fuel. Compared to gasoline, diesel fuel has 12% more heat energy. A diesel engine also allows for more efficient combustion. Because diesels draw only air into the cylinder, there's usually more air present during combustion. Now, this fact, coupled with the greater compression ratio of the diesel, means that the engine is able to make more complete use of its fuel. Overall, diesel engines average 30% greater fuel economy than comparable gasoline engines. Microprocessors, electronic fuel injection, diesel technology. These are some of the ways the internal combustion engine has been made more efficient. But what about power? There are ways of extracting more power from a given engine size. One of these is turbocharging. What is a turbocharger? Well, it's nothing more than a sophisticated blower which is driven by turbine blades. The engine's hot exhaust gases are used to power the blades. The turbocharger pumps more air into the engine's cylinders, thereby increasing the concentration of air and fuel. This results in more power from the same displacement. This system captures the energy in the exhaust gases that would otherwise be lost and transforms it into additional power. Making the internal combustion engine more efficient and more powerful. These are important steps in meeting today's challenges. In addition to the challenges of greater fuel efficiency, there are other considerations for automotive engineers, including controlling exhaust gases. Now, some time ago, exhaust gases were identified as major contributors to air pollution, particularly in areas with heavy vehicle populations. Engineers developed two basic methods of controlling emissions. One way is to make the combustion cleaner or more efficient. Another is by cleaning up gases released through the exhaust. Both approaches required extensive modification of the engine and exhaust system. One of the major breakthroughs of this effort was the development of a new device built on an old scientific principle. a catalytic converter. In many of today's vehicles, three-way converters are used. This type is made up of honeycombs coated with three rare metals: platinum, palladium, and rhodium. These metals are the catalysts that promote a chemical reaction without being permanently changed themselves. The converter controls the three principal emission components: hydrocarbons, carbon monoxide, and nitrous oxide. Through its catalytic action, it changes carbon monoxide and hydrocarbons to carbon dioxide and water. Also, the catalyst changes the nitrous oxide to nitrogen and oxygen. All are principal components of the air we breathe. These complex chemical reactions will only take place if the air-fuel mixture in the combustion chamber is in exactly the right proportions. This is constantly maintained by the onboard microprocessor. By fine-tuning the engine, combustion is maximized so that today's engines are not only cleaner, they also use fuel far more efficiently than engines of 20 years ago or more. Well, for example, emissions from the typical 1960 Chevrolet went uncontrolled. Virtually 100% of all spent gases went unchecked. Significant improvements have been obtained by 1974, the year prior to the introduction of the catalytic converter. Yet when the computer and converter technologies are joined together, today's Chevrolets, on the average, emit 96% fewer hydrocarbons and carbon monoxide, and 76% less nitrous oxides than their 1960 forebearers. This is a true American success story. Extracting more power from less displacement, marrying the internal combustion engine to the microprocessor, state-of-the-art technology in fuel delivery systems. What lies ahead in our quest for greater efficiency? Well, after harnessing the power of the sun, who knows what limits there are to man's ingenuity? While harnessing of the engine's power is important, transforming it into a usable form is just as critical. This is true of all modes of transportation. What's really happening here? The bicyclist's body is burning calories of energy as his legs provide the power to turn the crank connected to the chain sprocket. He is, in effect, the engine that powers this machine. And right now, the effort is rather comfortable. The road is smooth, the terrain is flat, and he's moving right along. Under these conditions, the gearing between the engine, the cyclist, and the load conditions of this machine are in harmony. That's fine, as long as the road is flat. But when he starts up an incline, he begins working harder and overheating. What's the solution? Simple. He just selects another gear. Now he's not working as hard, even though he is pedaling faster. The principle at work here is torque. But what is this force? Let's take a closer look. Out on the flat road, the gearing of the bicycle was set up to maximize speed. Now notice that the gear that's attached to the pedal is several times larger than the one that's attached to the rear wheel. The result is fewer turns of the large gear in relation to the smaller one. In other words, the wheels of the bicycle turn faster than the gear that drives them. Now, in power transfer terms, this maximizes cruising speed, but offers very little torque or power to climb hills or accelerate. That's why the cyclist had to change gears. But what really happened? Did he suddenly get stronger? No. He compromised. He gave up speed for torque, and he gained the ability to climb the hill. The relationship of the two gears changed. Now the driving gear is smaller, and the driven gear is larger. Now this means there's an increase in pedal turns and a decrease in revolutions at the rear wheel, or less speed. But though there's less speed, there's more power or torque. This is the same process in principle that takes place in a car or truck transmission. This is where the power of the engine is harnessed and the torque managed.
From a standing start, the engine engages with the transmission in low gear to produce lots of torque, to overcome inertia and provide acceleration. Intermediate gear provides a little less torque, but builds speed. In certain Chevrolet transmissions, 2 or more intermediate gears provide greater torque and speed flexibility. In high gear, or final drive, the engine and transmission output speed is the same. Torque requirements are minimal, and the vehicle speed is at cruising. Should the vehicle encounter a steep hill, its speed would decrease. Increased torque would be required to climb it, and the transmission would shift to an intermediate gear to compensate, just as the bicycle rider did. On a stretch of flat road, some transmissions have an available overdrive gear that allows the engine to turn fewer revolutions than the drive shaft. Overdrive results in better fuel economy and less engine noise.
When torque is required, a downshift to a lower gear is necessary. Now, in order to change gears, we need some way of disengaging the direct connection between the engine and the manual transmission to allow the gears to slide and mesh with each other and to move the vehicle from a standing start smoothly. The device designed to accomplish this task is the clutch. Essentially, the clutch is a sandwich of friction material between 2 round plates, one connected to the engine, the other to the transmission. Both are engaged by heavy springs that can be released gradually to move the vehicle from a stop. When the clutch is fully engaged, there's a mechanical connection between the engine and the transmission. An automatic transmission uses the principles of hydraulics for a smooth transfer of power between the engine and transmission without the need of a clutch. A fluid coupling, better known as a torque converter, is used. Now, this is essentially 2 sets of fan blades facing each other in a petroleum fluid. As the driving fan attached to the engine rotates, it pumps fluid into the driven fan attached to the transmission, causing it to rotate. Because there's no direct mechanical connection between the two, there is slippage between the driving fan and the driven fan. This slippage is required for gear changes during acceleration, but it can be a source of wasted power at cruising speeds. Engineers evaluated the situation and came up with the best of both worlds, the torque converter clutch. Above certain cruising speeds and under specified load conditions, the torque converter clutch engages automatically, providing a direct link between the engine and transmission. This link allows 100% power transfer from the driving fan to the driven fan. When speed or torque requirements change, the clutch disengages, the torque converter resumes its normal fluid coupling mode. Automotive research is aimed at even greater advances in transmission efficiency with something called the continuously variable transmission. In this unique system, the engine speed would remain constant. The necessary torque for acceleration and gearing for highway speed would be provided by the transmission. Now think of it. Instead of accelerating the engine to gain speed, you merely change gears. It's an extremely efficient way of transferring engine power and conserving energy. And it's something we can all look forward to.
General Motors wind tunnel. Considerable investments in terms of dollars and man-hours have been made here, studying the effects of air moving over a vehicle. This is the laboratory where the science of aerodynamics is applied to the design of tomorrow's Chevrolets. Why the investment? Because in terms of increasing a vehicle's efficiency, no other factor has as great an impact or degree of control as aerodynamics.
Moving through the air exacts a cost. The difference between 20 miles per hour and 60 requires 27 times the horsepower. At 55 miles per hour, more than half of the vehicle's power is used to overcome air resistance. At 70 miles per hour, the power required is almost doubled. Any design improvement, any adjustment of body contours that helps a vehicle slice through the air a little easier means increased efficiency. You see more of this influence every day on all sorts of vehicles, and the future holds a great deal more. Aerodynamics is the study of how air moves over the surface of an object. The more aerodynamic a vehicle's shape, well, the less it has to work to overcome the air's resistance. The vehicle design process begins with an analysis of basic shapes and the aerodynamic efficiency of each. The measure of this efficiency is expressed in the term coefficient of drag, or CD.
When placed in a stream of air, geometric shapes all have predictable coefficients of drag. The number can range from 1.8 for an aerodynamically inefficient cube to 0.005 for one of the most efficient shapes, the airfoil. But when these shapes are applied to vehicle designs, we find some remarkable contradictions. For example, how can it be that this large van has the same coefficient of drag as this small sedan?
Because this number doesn't take into account the vehicle's size, in particular its frontal area. This refers to the vehicle's total area presented to the flow of air, a cross-section of the vehicle's front view at its highest and widest point. Why is this important? Because frontal area is a major component of the vehicle's total drag as it moves through the air. That's why a vehicle with a big frontal area can often have an impressive coefficient of drag number, but still consume large amounts of energy needed to overcome its overall drag at highway speeds. A very large part of the downsizing effort in today's vehicles is to keep this frontal area to a minimum, as well as enhancing the design to part the air smoothly. Some of the findings made during wind tunnel testing can result in subtle yet effective enhancements to vehicle design. Sharp lines along fender edges are detrimental, and even minor things like mirrors or gaps between the doors and fenders affect the vehicle's aerodynamic efficiency. Open side windows can increase drag by 10% during highway driving. A wedge shape can help reduce overall drag. The angle of the windshield is a critical factor. A steeper angle helps minimize drag. Angling the vehicle downward about 1 degree is optimum for increasing aerodynamic efficiency. The addition of a rear deck lead spoiler also reduces drag. The use of a front air dam significantly reduces drag and lift by reducing air pressure under the vehicle, where turbulence is great. This turbulence is caused by an irregular underbody configuration. Channeling air around the vehicle thereby reduces air breakup and turbulence. Ideally, a vertical air dam should completely shield the front tires and have minimal ground clearance. Aerodynamic drag affects other vehicle performance factors besides fuel economy. A good aerodynamic design also contributes to a quieter ride because wind noise decreases. Windows will be cleaner because there's less road dirt accumulated, and there'll be greater vehicle stability in crosswinds. It even improves traction by creating a downward force, counteracting the natural tendency of most vehicles to increase lift at cruising speeds. The science of aerodynamics applied to vehicles is just beginning to make great strides in developing styling philosophies that mirror efficiency and economy.
Managing energy. This is only a fraction of the total picture confronting the automotive engineers. For if all these engineers who designed Chevrolet cars and trucks had to be concerned about was applying the engine's power in a straight line, their task would be a lot simpler. But in the driving environment, you don't always go straight. You have to maneuver quickly and precisely. and that requires handling, or more accurately, directional control.
The most crucial factor in directional control is the tires. In fact, the role of the tire is so important that suspensions are often designed around it. Now, one of the most sophisticated handling cars ever built, the Corvette, was designed in just this way, from the tire up. The challenge of tire design is that it must often embody what seems to be conflicting performance characteristics. It must have strength to resist damage, and yet still be pliable enough to cushion impacts. It should have a smooth surface for maximum contact on dry road, and a pronounced tread pattern for handling in wet weather. And it should be soft for good traction and hard for durability. So every tire design is really a combination of these needs. Dramatic advances in tire technology have been achieved in recent years to develop the best possible all-around tire. There are two basic designs, bias ply and radial tires. Bias ply tires usually have from 2 to 8 plies. The ply is a layer of rubber-coated fabric. The layers are made up of cords that cross at an angle, or bias. This angle affects riding comfort and steering accuracy. The larger the angle, the greater the riding comfort. The smaller the angle, the better steering accuracy. To strike a balance between these characteristics, most bias ply tires have angles somewhere between both extremes. Radial tires represent a breakthrough in tire technology. Instead of crisscross patterns in the plies, radials have parallel plies that radiate from one side to the other, crossing the center of the tire. This design offers a flexible sidewall for a soft ride, but only limited directional control. This problem is solved by crisscrossing fabric or steel belts around the tire, which results in better handling characteristics. The benefits of the radial ply tire include greater cornering capability because the flexible sidewall allows the tread to stick to the road and not skid. And because the belts reduce the distortion of the tread, handling capabilities and tread life are increased. Radials also offer a significant increase in fuel economy over bias ply tires. Less rolling resistance from radials can mean a 5 to 7% improvement in fuel economy. Tires are not only a key factor in any vehicle's handling characteristics, but they also provide a primary line of defense against road shocks. But even so, if the tires were connected directly to the vehicle, it would be uncontrollable and literally shaken apart as it was driven down the road. What we must have is a suspension system to keep the wheels in contact with the road, smooth out the bumps, provide the necessary directional control during acceleration, braking, and cornering, and support the weight of the vehicle and its cargo. Suspension and handling engineers strive to design the suspension so that it supports as much of the vehicle's weight as possible. The more weight that's suspended, the less shock that's transmitted to the passengers, and the greater ability of the vehicle to maintain control. In designing suspension systems, the ideal spring would be one that absorbs shock rapidly and returns to its normal position slowly. A single spring by itself cannot perform both functions in a vehicle. The solution is to use a spring that absorbs shocks rapidly and combine it with a shock absorber, which slowly returns the spring to its normal position. The shock absorbers used on vehicles are similar in construction to a familiar door closer that you probably have on your screen door to keep it from slamming. So as you see, the shock absorbers are really misnamed. They only limit or slow down the spring's return. The springs do the actual job of absorbing road shock. The springs and shock absorbers can be arranged in several configurations. One of these is an independent front suspension, where each wheel is attached separately to the frame by an upper and lower control arm. The spring and shock are mounted between the arms. Now, this arrangement allows an independent wheel movement up and down so that both tires retain better contact with the road and a more level ride. A variation of this suspension is the McPherson strut. It combines the coil spring and shock absorbers into one unit,
The coil spring is attached around the upper half of the strut, and a shock absorber is mounted inside. The result is more efficient packaging of the front suspension components and reduced weight, which are important considerations in today's smaller, lighter Chevrolets.
But as effective as all these components are in suspending the weight of a vehicle and absorbing road shocks, there are other forces that must be dealt with. In a turn, for example, centrifugal or outward force is generated, causing the vehicle to lean. To counteract this tendency, a stabilizer bar is used. It runs across the vehicle from one side to the other, twisting as the vehicle leans. This resists that lean and helps to keep the car level. The stabilizer bar also helps keep the tire flat on the road during cornering. Modern designers continue to strive to create a vehicle designed to deal with all handling forces. This is the objective as they work toward the creation of that impossible dream, the perfect car and truck. Since the invention of the wheel, man has dealt with the problem of moving weight. Over the years, many types of vehicles have evolved to meet the requirements of various loads. Around the turn of the century, a country doctor may have ventured out and hitched his horse to a carriage similar to this. Now, this vehicle was obviously designed to carry passengers with as comfortable a ride as possible. In the 18th century, the term truck was first used to describe a wagon designed to carry weight. They used thick slabs of wood like this, reinforced with heavy iron. And the suspensions were designed for carrying weight, obviously not for comfortable transportation. The need to carry more weight, faster and more reliably, increased as the days of animal horsepower diminished and the cities grew. The novelty of the horseless carriage quickly transformed into the serious business of automobiles and trucks. Now, these developments coincided with technological advancements that provided more powerful engines and new suspension designs capable of carrying larger cargoes. The key to a vehicle's load-carrying capacity is the assembly known as the chassis, which includes the frame, axles, suspension, wheels, and tires. The basic component of the chassis is the frame, the backbone of the vehicle. Some cars and light-duty trucks have an integral body and frame structure, while others have a separate frame to which the body is attached. A vehicle's load-carrying capacity can be no stronger than its frame. All chassis components are attached to it. The frame's strength is determined by two factors, design and materials. The design can be channel-shaped, box-sectioned, or a unitized body frame with various depths, widths, and thicknesses that can be incorporated to meet the load requirements. The strength of material used in the frame is expressed in a number of terms, such as yield strength, which provides a measure of the metal's ability to withstand load forces. Front and rear axles alike are rated by their load-carrying capacity. Now, this capacity is not determined solely on the strength of the axle, but rather as part of a system, including the axle springs, shock absorbers, tires, and wheels. There are three types of springs in common use: coil, leaf, and torsion bar.
Coil springs are simply coiled steel rods that absorb shock by compressing and expanding. They are normally used on the front and rear suspension of passenger cars and on the front suspension of trucks. Leaf springs consist of steel leaves of varying lengths that are clamped together. The long, flexible leaves handle the weight of the vehicle when it's empty or lightly loaded. The short, stiffer leaves come into play when the vehicle is heavily loaded or the road is rough. Trucks usually employ leaf springs in the rear because they're effective for heavy loads. Torsion bar springs absorb shock by twisting. Many Chevrolet four-wheel drive trucks use torsion bar springs to cope with the rough conditions encountered in off-road driving.
The final component of the chassis is the wheel-tire combination. When we're talking weight capacities, the wheel is not rated specifically. Rather, it's matched with a tire chosen for its load-carrying ability. The tire's rating is designated by the term load range, usually imprinted on the tire. The load range is an indication of the tire's strength, represented by a letter, A or B, primarily for passenger cars, or C, D, or E, which are rated for heavier loads, such as those for trucks and trailers. The weight-carrying characteristics of a design are only half the story of weight management. Materials used in the design and construction of a vehicle also play an important role in helping to move cargo efficiently. Overcompensating with too much material, too much weight, can severely handicap a vehicle's ability to move cargo at a reasonable cost. And the high technology age has certainly helped the cause. The use of tough, lightweight alloys, plastics, fiberglass, and even ceramics help to reduce structural weight without necessarily reducing interior dimensions or cargo capacity. Well, for example, this monoleaf spring was designed to have the same weight-carrying characteristics as the old design, but weighs 33 pounds less. Plastics and lighter metals have played an important role in maintaining structural integrity while providing tough, lightweight designs. Interior trim and components, engine parts, even fuel tanks have been carefully studied and redesigned where feasible. The result is substantial weight reduction without sacrificing load capacity and stress tolerance. This translates into reduced power requirements, which in turn allow the use of smaller, more fuel-efficient engines. The fragile balance of load-carrying capability and efficiency has become more and more attainable. There are two ways of looking at weight management: the weight of passengers and cargo, which is the weight-carrying capability of the vehicle, and the weight of materials used to build the vehicle, incorporating designs and materials into a structure that will support the load without overcompensating. A perfect balance of weight and efficiency. It's not there yet, but they're working on it. Our increasing dependence on machines in our everyday life has created a whole new field of scientific endeavor called ergonomics, the study of the mutual adjustment of men and machines. In other words, how we as people relate to machines, and vice versa. In the case of motor vehicles, as we work to make them more fuel efficient, designing the space available for the driver and passengers becomes more and more of a challenge. In vehicle design, it's the human factor that ultimately defines the vehicles. Now, people requirements for space, visibility, control, entry, exit, comfort, and security determine everything, from where a radio knob will go to the total size of the vehicle. But before any of these kinds of details are determined, even more basic questions have to be answered. For example, is the vehicle primarily for passengers, cargo, or a combination of both? How many passengers? How much cargo? Off-road use or strictly a highway vehicle? What are the maximum and minimum heights of those expected to drive the vehicle? As these questions are resolved, the design begins to take shape. Chevrolet's objective is to optimize the man-machine relationship. In other words, the ergonomics must be right. The key is the human factor. Since we come in all sizes and shapes, from a 5'2" teenager to a professional basketball player reaching 7 feet or more, engineers need to determine the optimum placement of controls, seat adjustments, and lines of sight that will accommodate the vast majority of American drivers. To do that, engineers have precisely measured thousands of people using this machine called an anthropometer. it can provide them with a precise, accurate description of the physical makeup of the American driver. Using this data, engineers can ensure that interior features are usable by 95% of the population. That's the objective, 95%. This use of ergonomics and space-efficient design techniques has become increasingly important in recent years. The industry's commitment to fuel-efficient vehicles has had a tremendous impact on interior design, on space utilization. Now, one of the easiest ways to improve fuel efficiency is to reduce vehicle size and weight. A smaller car or truck burns less gas. Simple. But as vehicle size was reduced, engineers had to rethink the conventional front engine rear drive configuration that was the industry standard. In smaller cars, a front-wheel drive arrangement with the engine mounted crossways or transversely produces several advantages connected to space utilization. For example, to make room for the engine, upper control arms in the front suspension are eliminated. This allows for a lower hood line to reduce aerodynamic drag. The compact packaging of the engine, transmission, and drive components reduces their intrusion into the interior space. The transmission hump in the front compartment is smaller, and the drive shaft tunnel in the rear disappears. As vehicles grow smaller and lighter, unitized body frame construction is replacing full perimeter frames. This allows space formerly occupied by the frame to be used for passengers and cargo, at no sacrifice to the vehicle's structural integrity. While vehicles were shrinking on the outside, they still had to provide adequate passenger room. That meant redesigning all sorts of components, well, even window mechanisms, so that, in turn, the thickness of doors could be reduced, freeing up more interior space. This totally new approach to space utilization involves everything from the seemingly insignificant window mechanism to major reconfigurations of the engine and drivetrain package and design of the interior compartment. It's no wonder that today's vehicles are often referred to as being reinvented. What's next? Well, if history is any indicator, we'll continue to see an emphasis on fuel-efficient designs that put a premium on weight savings and better utilization of space. But, as has always been the case, it'll be the human need that makes the final determination of what tomorrow's vehicles will be. Concepts, ideas, dreams. This is how they come together. Whatever you call them, they're here. Translated into metal, fiberglass, and plastic. Referred to by exotic names such as Aerovet, Stingray XP87, Manta Ray. Vehicles of the future. From a perspective cast decades ago, a time when turbine power seemed like a viable alternative. But that was before emission standards were enacted. Some thought that rotary power was the answer for greater performance in a compact design. But that was before the emphasis on fuel efficiency. Government-mandated bumper height and impact standards conflicted with many designers' flowing lines. Does that negate the value of these concepts? Hardly. Because much of what we know today about the aerodynamic effects on vehicle design was learned during the development of these idea cars. The same is true of the lighter weight materials, alloys, and plastics used in our present-day vehicles. The benefits derived in fuel efficiency alone more than compensates for the investment made in these dream cars. You know, it's hard to believe that the technology reflected in this design is more than 2 decades old. But much of what was experimental then is now commonplace. Well, disc brakes, for example, were a rarity in the mid-'60s, and the opposite is true today. So what does the technology of today portend for the future? In a word, excitement. The Aero 2002 concept car, a 4-passenger experimental subcompact, This vehicle features front-wheel drive and an aerodynamic shape with a coefficient of drag of 0.230. Among the advances incorporated into the 2002 is a 4-point air suspension system that lowers the vehicle closer to the ground during high-speed driving to enhance its aerodynamic qualities. Perhaps a feature we'll see on future production cars. A completely new and different type of vehicle is the lean machine. It takes its name from a slender silhouette and the capability to lean into a turn. It can also travel up to 200 miles on a gallon of gasoline. Somewhere between the Aero 2002 and the lean machine is the TPC, or two-passenger commuter, a vehicle that delivers up to 95 miles per gallon highway and 68 in the city. Its small size and maneuverability make it an ideal urban car. Does the future offer anything more than aerodynamics and fuel efficiency? Remember, the key word is excitement. Dreams, ideas, concepts. This is how they all come together. Where the ingenuity of man deals with the laws of nature and bends them to his will to produce a mobile society. People in motion. What lies ahead? Well, it's hard to say. But when it comes, I sure want to be behind the wheel.